All right, welcome to another episode of Science with Surback. Subscribers, I'm glad you're back in action here. And today what we're going to be talking about is section 13.3 that deals with energy. So, before we get started, I just want to outline a couple of objectives of this section. So, objective number 1, you should be able to determine the relationship between energy and work. Objective 2, determine why potential energy is called energy of position. Objective 3, determine the factors of kinetic energy. And number 4, objective 4, is to determine what non-mechanical energy is. All right, so we start out here with energy. And energy is defined as the capacity or ability to do work. So I'll write this down. All right, so there it is, written down, the definition that is. And so a couple of things about energy. One, this is different from work in that we have these terms capacity or ability to do work. Now remember, to do work, you had to have an object in motion, had to have some sort of movement. Now with energy, we have a broader term because we have this capacity to do this work. Now, whenever the work is done, energy is transferred when work is done. All right, so with energy, there are two main ways that it can be measured. Number one, we can measure energy for an object at rest. Now, we're going to learn that this measurement of energy for an object at rest is eventually going to be this potential energy or energy of position. So, this is very different from work because in work, an object must be in motion to be measured. So let me write that down. All right, so there's that written statement right there. Now, the other way that we can measure energy is we can measure energy for an object that is transferring energy. Now, what we call here when energy is transferred from one object to another is this energy in motion. Now, the way we measure this second type of energy is we measure how much work is done on a receiving object. All right, so we talk about the ways here to measure this energy. We can actually specifically define these two ways we measure energy into two different types of energy. So the first type of energy that we have is potential energy. Now, potential energy is defined as the energy that an object has because of the position, shape, or condition of the object. Now, within the category of potential energy, there are two distinct categories of potential energy. The first of these two categories is elastic potential energy. And the best way to describe elastic potential energy is with something like a rubber band. A rubber band is going to stretch back and forth. Now, specifically, this is defined as any object that is stretched or compressed to increase or decrease the distance between its parts of the system. So I'll take a moment and write that down. All right, so there is that definition of elastic potential energy. Now, this B/T is just another way to express between. The other type or category of potential energy is gravitational potential energy. And so gravitational potential energy is just defined as any system of two or more objects separated by a vertical distance that has potential energy. Now, I'm going to pause the video and I'm going to write that definition down. All right, so there is that definition, and I know I gave it not a whole lot of space there, but we have a formula for gravitational potential energy, which we will talk about here in a second. The other thing I want to make is a point about an example. The best way to describe gravitational potential energy is a roller coaster. A roller coaster goes to the top of the hill. It has potential energy to be transferred to moving energy at that top of the hill. Because there's a vertical height from the hill, it has that gravitational potential energy. So let's go ahead and move on to an example of potential energy. So in our example that we have on the second page here, we want to know what is the gravitational potential energy of an object that has a mass of 1,200 kilograms and it's on top of a hill that is 42 meters high. So, as I mentioned on the previous page, there is a formula for potential energy. And so the formula for potential energy is PE for potential energy is equal to the mass times the g for the free fall acceleration and or gravity, and then it's going to be multiplied by the h for height. Now, out here to the side, the PE just stands for potential energy. The M is going to stand for the mass, and that mass is going to be in units of kilograms. Now, I forgot to mention the energy. The unit for energy is going to be J for joules. And then our G is our free fall acceleration due to gravity. Now, on Earth, we have the same g, or we have the same free fall acceleration. And so on Earth, that free fall acceleration is always going to be 9.8 meters per second squared. And that will be pretty consistently used throughout this chapter unless I say we're on a different planet. Now our H is just going to stand for height, and that height has to be in units of meters. So the higher a roller coaster is, the more potential energy it has because we increase that particular height. Now, if we get back to this example here, we want to know ultimately what is our potential energy. There is nothing mentioned in this particular problem about potential energy, so this becomes our question mark. Our M for mass needs to be in 1,200 kilograms, or excuse me, needs to be in kilograms, and so our mass is listed at 1,200 kilograms. Our G, we are assuming that we're on Earth. Unless it says we're on a different planet, we are going to be on Earth. So our G is going to be 9.8 meters per second squared. And then our H for height has to be in meters, but this roller coaster, this car, is at a height of 42 meters. So for our potential energy, again, we don't know it, so we just write it in as PE, is going to be equal to 1,200 kilogram times 9.8 meters per second squared times 42 meters. Now, all I'm going to do is multiply these numbers across, and I'm going to obtain my potential energy in joules. All right, so like I said, all I'm going to do is I'm going to type what I have written right here into my calculator. So I'm going to take 1,200 times 9.8 times 42. Now I get this big, large number, and I'm going to do some rounding here. And the number I'm going to round to, I'm going to only use 2 significant digits. So when I round this particular number, I am going to round to 49, and then I'm going to put all these zeros behind it. So it'll actually end up rounding to 490,000. So our potential energy is going to be 490,000, and our units for that is J for joules. Now, oftentimes what you'll see here is that this will also be expressed as kilojoules. That makes this number a little bit more reasonable. Moving on here to our second type of energy, this right here is our kinetic energy. Now, kinetic energy is just simply defined as the energy of an object due to the object's motion. So, with our kinetic energy, there is a couple of things to note here. Number one, an object in motion is both doing work, or has the ability to do work, and has kinetic energy. So I'm going to put this. A moving object has ability to do work, and it has kinetic energy. Now, this value for kinetic energy is going to depend on the speed and the mass of a particular object. And we'll see that when we introduce that particular formula. Now, before we introduce that formula, there is one additional thing to think about, and we tie this back to chemistry, and that's kinetic energy of these atoms and molecules that surround us and make up everything. And so, if we think back to chemistry, remember that the atoms and the molecules are constantly moving and they have a mass. So because they are constantly moving and they have a mass, all molecules and all atoms are going to have some form of kinetic energy. So my point about this is that atoms and molecules have kinetic energy because they have mass and are moving. So something to consider if you study chemistry further and further. Now, the formula for kinetic energy. Our kinetic energy formula. The formula here is going to be Ke for kinetic energy is equal to half times m for mass times v for velocity squared. So again, let me define these terms here. Our Ke is the kinetic energy, and kinetic energy is expressed again in joules. The m is for our mass in kilograms, and then our v is for velocity. And velocity here, velocity is meters per second. So we get down here to our final part of section 13.3, and we have a 35 kilogram child. They're outside enjoying the snow. They're on a slide, or maybe a hillside if they're sledding, and they go down a hill, and at the end of the hill, that sled and that child had 190 joules of kinetic energy after they slid down the hill. We want to know, what is the child's speed or velocity at the bottom of the hill? So again, we're going to use this same formula that we just talked about a couple minutes ago, and we're going to do some plugging of these numbers that we know and solve for what we don't know. So just as a reminder, the kinetic energy is equal to half times m times v squared. So kinetic energy is expressed in joules. In this problem, and I almost caught myself there, in this problem, we have the joules listed at 190 joules. Now our next variable is the mass. The mass of a child and that sled is 35 kilograms. And then the final thing is our v for velocity. Now, our v for velocity should be in meters per second. And if we double check this problem, there is no meters per second or no velocity listed. So this ultimately is going to be our question mark. Now, we're going to plug these numbers back in. So 190 joules is equal to half times the mass, which is 35, times our velocity, that's going to be squared. Now, we have to be very, very careful because we have this squared term. So what I am going to do is I am going to get rid of everything that's attached to the v squared by doing this. I am going to divide by half times 35. That's so I can isolate v by itself. And I'm going to divide that on each side. So what we need to do is this. We have 190. And so what I'm going to do, I am going to insert 190 for our joules on top, and I'm going to divide it by half. Now remember, half, it can be written like how I have down here on the paper, or half is simply 0.5. Then I'm going to multiply that by that 35 kilograms, the mass of the child, and I'm going to close the parentheses. Parentheses is key, or the order of operations will take over. So I hit enter on my calculator, and I get this big long decimal. And I'm going to write down, right now, I'm going to write down 10.86. So I get 10.86 equals our v squared. Right now, this is not the velocity of that particular child because we have to get rid of this squared term. So to get rid of a square term, what we have to do is we have to take the square root of both sides. So when we do this, we hit second, we go down to the square root, and I'm going to insert this number right here into my calculator. Close the parenthesis, and I'm going to hit enter. So I'm going to round to 2 total digits. So in this case here, my number is going to round to 3.3. 3.3, the units for velocity is meters per second squared. And then you have to think velocity. This right now is only speed. Velocity also includes directions. So this is 3.3 meters per second downhill. We have to include that direction because it is velocity. And this finally equals our v. All right, so I packed a lot of info into section 3. There's a lot of good mathematical equations here. I hope you've enjoyed this video. If you have, like, and as always, remember to subscribe.